Alright, welcome to a new series on thermodynamics. My name is Eli and I'm currently studying mechanical engineering. I really like thermodynamics and I wanted to kind of teach it a little bit, but I don't really want to be a teacher or a professor, so I thought this might be the easiest way for me to do it. This isn't going to be the most extensive list of subjects in thermodynamics. It's not going to cover everything you're learning, but it is more than likely going to cover some topics that I think will give you a little bit of trouble. And if there are subjects that you kind of want me to cover because you're kind of having trouble with them and I don't cover them, by all means let me know in the comments and I'll see how I can help. So for this first episode, we're going to cover linear interpolation and dimensional homogeneity, which I had to be sure was spelled right because it wasn't at first. And these aren't really thermodynamic subjects, but they're used a lot in thermo. These are just like math concepts. They sound really convoluted and complicated, but once you really get into it, it's not that bad. So let's go ahead and define a couple things real quick. What is linear interpolation? And it might just be best to draw it, is essentially just an estimation of a value. So let's say you're given 2 points, and you're given that the first point is right here, second point is right here. Now if you're asked to find the corresponding value to this independent variable right here, you would take this slope, and you'd say, well, it's probably going to fall right here. Depending on like the data set and like the order, the polynomial, whatever, it can have a lot of error. Before this class, it's actually pretty accurate most of the time, so we're good. There are calculators and all that that will give you the exact enthalpy, and it's great. But for this class, you're not going to really need it. Dimensional homogeneity just sounds like a cool concept. It's like something you throw out in like a party, and you're like, oh yeah, dimensional homogeneity, and people are like, wow, you're so smart. But it's really simple. It basically just means units have to match. You multiply a Newton and a meter, you get a Newton meter. But if you add a Newton and a meter, you get confused. You can't add Newtons and meters. You can add Newton meters and Newton meters, and that'll give you Newton meters. Dimensional homogeneity also includes like just matching units. So like if you have, for example, kilograms on one side, you're not going to have just seconds on the other. You'll see dimensional homogeneity in a lot of problems, like with ideal gas law when you have to convert units, but we're actually going to see it in this linear interpolation problem, which is great because we're just killing two birds with one stone. We're basically given two data points, one at a temperature of 10 degrees and one at a temperature of 20 degrees, and you're given these enthalpies of 262.4 and 270.9, and you're asked to find the enthalpy corresponding to a temperature of 17 degrees Celsius. And we're going to start with the equation for linear interpolation. And as I kind of stated, we're estimating something based on a slope. So if you look, this guy right here is actually the equation for slope. This guy is kind of just like giving you like an approximate, like how far off is the independent variable for the value you're looking for from the initial value. Y1 is just like a lower limit. Y is obviously going to be our dependent variable, and in this case, Y is going to be enthalpy. The x values are going to be temperature. So you don't have to worry about what enthalpy means or any of that right now. We're just looking at the numbers right now. And so the green values, or the x1, y1, are going to correspond to the 10 degrees and 262 kilojoules per kilogram. And the red values, or the y2 and x2, are going to correspond to 20 degrees and 270.9 kilojoules per kilogram. This blue value is what we're looking for. So without further ado, let's just get plugging and chugging. So y, we still don't know, that's what we're looking for. Y1 is going to be 262.41 kilojoules per kilogram. It's not a y. Plus x, and this is going to be the value that we're already given for the data point we're looking for. So 17 degrees Celsius minus 10 degrees Celsius because it's the initial data point. So now we're going to do the slope, and y2 is going to be the second data point, which is 270.89 yikes minus the first data point, and this is going to be really messy just because I don't have a lot of space, but it's going to be what, 262.41. And these guys, their units agree. They're in kilojoules per kilogram. And then we're going to divide it by the independent variables, which are just going to be the temperature. So it's going to be 20 minus 10 degrees C. Then we're going to close it off. And hopefully you kind of understand where we got these numbers from. If there's any confusion, just let me know in the comments and I'll clear it up a little bit. So now we're going to look at the dimensional homogeneity of everything. We're going to make sure that the units agree with each other. So what are we doing here? We have kilojoules per kilogram plus Celsius times kilojoules per kilogram over Celsius. But let's go ahead and look a little closer just at this guy over here. We have Celsius times kilojoules per kilogram over Celsius. So basically we have Celsius over Celsius. We're left with kilojoules per kilogram plus kilojoules per kilogram. And what we're looking for in the end is enthalpy, which we know just from the table is in kilojoules per kilogram. So what it means is the units agree, the units match, we can add them, we're not violating math laws. We're just going to plug in our numbers. We should get a value of 268.346 kilojoules per kilogram. Does this make sense? It should, right? Because it's more than 262, which is like the lower bound, but it's less than the 270, which is the upper bound. But you've done it. You have now learned linear interpolation and dimension homogeneity. I hope this helps, and I hope you'll stick around for the future videos because we'll get into some actual thermo soon.